Okay, so let's start. See how much you guys remember. So what is the difference between organic chemistry and inorganic chemistry? Was that carbon? Okay, yes. So carbon is the major component that makes something that's going to be organic. There are a couple molecules that kind of go both ways. One of those is carbonate. Do you guys remember what carbonate looks like? Let's see. Israel, are you there?
Yeah.
Okay. So do you guys remember what carbonate looks like? No one? It's the carbonate ion, you're right. CO3, 2 negative, that's right. Okay, so carbonate is one of those ones that organic chemists don't really claim. Well, they claim sometimes, right? The fact that it does have a carbon in it, they'll claim it, but in reality, or inorganic chemists also claim it as well. So another one is cyanide. Do you guys remember what cyanide, the cyanide ion looks like? C what? CN. And what's the charge? -1, yeah. See, that's impressive, right? Because, that was all on your polyatomic ion tables, and, you never had to memorize any of it. They were all there. So you guys, it's pretty good. Okay. Today normally would not be a lecture. We would normally have labs, but I figure you need to read these labs because they're pretty in depth. And so you guys want to try to get a little familiar with it. We have some of the equipment. Actually, we have almost all the equipment that you guys need for the very first 2 labs. It's the 3rd lab that we're waiting for stuff to get here. So we may have to throw in some simulations just to kind of keep us going so we don't fall behind. And on those days that we may not have the equipment or the supplies in yet, then what we'll do is we'll do a double lecture that week, and then we'll just make up those labs. We'll put them all in once if we need to. Okay. So just to kind of give you guys the heads up. So today we're doing a lecture to kind of keep us going and kind of get us back into the game, because I know we're a little rusty. You guys have the whole summer off. Anybody do anything fun for the summer? Nothing? Just work? Well, I know about that. Okay. So we talked about organic and inorganic. Okay. So the definition of organic is going to change a little bit more in regards to how we're going to be perceiving it. Like, for instance, here we have ammonium cyanate. So in this case, this guy is going to be considered an inorganic mineral, right? Rather than an organic mineral where we have urea, which is organic. So we're going to add another little layer to it, right? And a lot of times we associate organic material, things that are coming from living organisms, okay? And inorganic materials often coming from like minerals and things to that extent. But bottom line, when we think about organic, it boils down to it if it contains carbon. So it's a compound that contains carbon. And both of these technically contain carbon, does it not? Okay, so what makes carbon so special? Why is it the building block of almost every living organism that we know of? It is the building block of every organism that we know of. Why? Why is carbon the building block of every organism that we know of? Or, in other words, why is carbon such a whore?
Isn't it because it can take or give electrons?
So the fact that it's right there in the middle, it can take or give electrons. That's true. Okay. So what else? What else is unique about carbon compared to some of the other elements that are to the sides of it? So it could share electrons, okay. And it's happy to share electrons. Why? Anyone? So do you guys remember the carbon-Lewis dot structure? Anyone? Boy, this is going to be a rough semester if you guys don't talk. Carbon, the Lewis dot structure for carbon. Anybody remember what it looks like? It's C with 4 dots. Okay, what does that tell us? Those C with 4 dots. How many more electrons does it need to? It needs 4. So in theory, carbon can hold up to how many different, let's say, hydrogen molecules? 4, right? So it gives it a lot of flexibility, right? So carbon has that flexibility. It can make at least 4 bonds, right? So if it's with another carbon molecule, it can sit there and bond with that and interact with it, right? So it gives it a lot more flexibility. You guys remember that, right? I know, it's rusty, huh? It's like, hey, you need to start brushing off that dust here. Okay. Okay, so that's what makes carbon so attractive. Okay, and let's see. You guys remember the structure of an atom? What's in the middle of an atom? Protons and neutrons. What makes up the mass of the atom? The protons and the neutrons. So what's involved in the reaction of an atom? The electrons. And so when we talk about those electrons, we talk about them, they're able to do, what can we do with those electrons? What is the way that we make reactions? And why do we want to make reactions anyway? So we could either give, we could take, or share. So by giving, taking, or sharing, we cause reactions to occur. Right? So reactions are that process of giving, taking, or sharing. Okay. So if we're giving, taking, and sharing, why do we need to give, take, or share? What is the benefit of it? Is it just because I want to do it? Oh, I like that. I love that answer. That is a beautiful answer. It does deal with the energy state, right? We want to be stable, right? We want to have low energy. Who do we know that is like kicking it and they're chilling, they're happy, they don't want to react with anybody, and they're always in low in energy? What was that? Noble gases. Okay, so all of the other elements are not noble gases, right? But they want to be like the noble gases because they have a much better energy state associated with them. So we do reactions to try to be like the noble gases, to try to get that so that our octet is full, so we're happy, satiated, we're chilling, right? So reactions occur to try to get to that lower energy state, okay? Let's see how much you guys remember. Let's see, the periodic table. Let me pull up the periodic table. I've been talking about the periodic table all week. You would think I teach chemistry or something. Let's see. So my favorite site, you guys should know it by heart. That's all we talked about. Screen. Okay, so let's say we have rhodium. So how many electrons does that have? The rhodium, RH. Okay. Okay. How many? You guys are whispering. You guys should know this. Come on, has it been that long? Sampula. 45. Yeah, 45. Israel's right on the board there. So 45 electrons, because we went over this yesterday. Better know it. I'm going to throw something at him through the. Okay, so 45. How many protons? 45. So you guys remember that upper number there? That number right there, that's called the what? What number is that called? What is it called? It's the atomic number. we know that that represents that atom. It tells us that atom is rhodium, right? So since we know that that's rhodium, we also know that that's the number of protons. Can we change the number of protons? No, we can't change the number of protons. The number of protons represent that atom, right? So this here is what? The atomic mass, okay? So it's the atomic mass or the molecular weight, right? Or the atomic weight. Okay, so we know that if we wanted to calculate the number of neutrons that it has, how would we go about doing that? Okay. So, but we need that whole number, right? So we need to get it, so it's that whole number, which is called the mass number, right? So how do I get it to the mass number? We round it. So it'll be 103, 103 minus 45. Boy, y'all are rusty. It's just like, huh? What is this? Okay, so we'd have 58 neutrons. So you guys remember that, right? Kayla, you remember that? Yeah? Okay, you guys are brushing off that dust, right? Okay, good, good. Okay, so you guys want to sit there and take that into consideration because we're going to be playing with a lot of this. Well, you won't be playing so much with some of the other chemicals, but in terms of carbon, you want to sit there and play a lot with carbon. Primary things that you guys are going to notice with carbon, it's going to be carbon, nitrogen, oxygen, and you're going to be making bonds with them like crazy, right? And they're going to be crazy type of bonds. They're going to be structures and surfaces, and there's going to be angles and things like that. So you guys want to remember the things that we've done because we're just going to be building on that, okay? So brush off those cobwebs, right? We need you guys present. Okay, let me see. Okay, let's go back to the slide. Let's see. So you guys are very familiar with isotopes, right? So if I was talking about carbon 13, what is the difference between carbon 13 and carbon 12? Number of neutrons, okay? How many neutrons does carbon 12 have? How many neutrons does carbon 13 have? Okay, because we know that all carbon 12, carbon 13, and carbon 14 all have how many protons? 6, right? Because we know the atomic number for carbon is 6, right? Okay, so that's just freshening it up, right? You guys remember that? No problem? Good, good. Okay, so let's see if we can make it a little. See what else you guys remember. So, do you guys remember orbitals? What is that? Oh, God, it's been a while, huh? Okay, so let's see. So the S orbital, atomic orbital, how many electrons can we hold in the S atomic orbital? I guess I shouldn't. So it'll be right there, right? 2, what about the P? What about the D? And the F? 14. And if we had a G, how many would it hold? Are you feeling confident? You got to speak up too. She said 18. Do you guys agree or disagree? Okay, so we said the S holds 2, the P holds 6, the D holds 10, the F holds 14, then the G would hold 18. Yeah. Well, technically there isn't yet, but as soon as we start finding more atoms or elements, we can go up there. Or as soon as we start making atoms and elements that are more stable, we'll be able to go there. That's the next level. So when you guys get into, we call it physical chemistry, PChem. When you get into physical chemistry, you guys will talk about that because it becomes more theoretical. There's things that, like quantum theory, the real aspects of quantum theory, which this deals with, but we don't, there's things that we don't know yet, but we're predicting. Okay. Okay. So, and you're familiar with where to find this on our periodic table, right? Okay, so in terms of energy levels, which one is lower in energy levels? The S, the P, the D, or the F? If they're all in the same period. S. The S has lower energy level than the P. P has lower energy level than the D. And the D has lower energy level than the F. So if you guys remember on the periodic table, do you guys remember how do we define it here? Where would be the S? Where would be the P? Where would be the D? Okay. So this would be the S. The P. The D. And the F. And we know that these two are technically in the D, right? You guys remember that? Okay. So now that you guys have grown up a little bit, I'm going to bust your bubble. Okay, you guys ready? These two are hot messes. There have been an argument for years, and it's been going on for years, whether they're truly in the D orbital or they're truly in the F orbital. It's been going on for years, we'll say, and it's still, they haven't been able to get a definitive answer, but the majority of the people believe that these guys are in the D. That doesn't mean that it's right, okay? Just to bust your bubble. Because I thought you guys all thought that chemistry was well defined, and you know, well, I'm just going to have to blow your mind with that. That's not the case. Okay. Technically, they are thought to be in the D. The majority of scientists today believe that they're in the D orbital, but there's some debate whether they're actually in the D or in the F. And it's been this huge debate. People got violent over it. Okay, let's see. Now I know this is all okay. So you guys you're familiar with the electron configuration. One electron is going to be going in the up direction. One is going to be going in the down direction, or spins, right? You guys remember that? So when we talk about our quantum numbers, right? Those quantum numbers are well, I should say, every element is defined by 4 quantum numbers, right? And so we have the period, which is the very first quantum number, or we call it the primary quantum number, right? We have the L, right, which is our angular momentum quantum number. We have the M quantum number, and that is the angular momentum. That's the one I always get. The angular momentum, and that's the one I always forget. I have to remember what it stands for. It'll come to me in a minute. And we have the S, the MS, which is the spin, the magnetic spin. So those are the 4 quantum numbers that define elements, right? And you guys know that every element has a unique quantum number associated with it, right? So for instance, let's go back to the periodic table, and then we'll talk about this. Okay, so say every element, I shouldn't say every element, every electron in an element has a unique quantum number associated with it. So for instance, this guy has 12 electrons, right? So each of those electrons have a unique quantum number that is associated with each one, right? So we went through, and we'd always go through, we'd have that 1s. We'd have the 2s. I know that fly is just pain. We have the 2p. I think I make sure you guys do this on the exam, if I remember correctly. I didn't make you guys do this on the exam. We have the 3s. Okay, so if we were talking about magnesium, we know that we have one that goes in this direction, that direction, this direction, that direction, this, and back the other way. Okay, so that would be magnesium. So this here, this particular electron has a quantum number of, it would be 3. The s orbital, so then that would be 0. And then it would be 3, 0, 0, because there's only one of them. And then it would be the magnetic spin minus a half for this particular one. You guys remember that? Okay. So that's correct. So it has a unique address. I like to think of it as like a little address, right? Because every house on your block has an address associated with it. They don't all deliver everything to your house, do they? No. Hopefully not. Otherwise, you got a lot of good Amazon stuff, right? Okay. How are you guys feeling on that? You guys, okay? Now, you're going to ask me, we're going to really need to know that for organic chemistry. No, but you need to be familiar with it. You need to understand that distribution of electrons, because that's going to play a part in terms of where we're going to attack at in terms of later on, which ones are going to be available for attacking and where we're going to attack at. Okay. So let's go back to our lecture notes. So here we've talked about the Offenbach principle, which basically says, those energy levels, we're looking and we're going to fill those lower energy levels first, and then we're going to move up to the higher energy. That's what it basically says. The Pauli exclusion principle, only 2 electrons could be in a it'll be an orbital, an atomic orbital. So like in the S, you have only 2 that are able to be in there. And like in the P, I guess I have it here. So you have the 3 orbitals here. So technically you have 2 electrons that are in each one of those. So you can only have 2 of them in there, and they have to be going in opposite direction, right? So we can have 0 all the way up to 2, and that's it, okay? And then there's the Hund's rule. Hund's rule basically deals with that degeneracy. You know how like we go down to the 3D, we have 4s, 3D. You guys remember that? Okay, so that's the Hund's rule. And again, we want to sit there and we will go through those degenerate components, but also the other thing is that when you're filling up that shell, you want to fill up in the same direction first, right? And so you're not going to have somebody right next to each other. So in other words, let's see, if I had my p orbital, this guy, this guy, this guy, each one would get 1 first before you go back and fill back in the other way, okay? Crash course, huh? Chem 1B, part of 1B, and 1A, I guess I did it both, depending on which semester. You guys remember Lewis dot structures, right? Finally, thank you. Okay, and we know that lithium is 1 away from being a noble gas, so it's going to want to get rid of that 1 electron. It wasn't dead. He was playing possum. She just needs to make sure. Okay, so we know that in the case of fluorine and chloride, those guys, they're 1 away from being a noble gas also, but a different way. They just need to gain 1 electron. Right? You guys remember that, right? Onita. Good. Okay. So in the case of the hydrogen, hydrogen is that special case. It wants to gain that one electron. It's happy to gain it. Or in the case of an acid, it wants to be H plus, right? So it wants to lose that electron. Okay. And we will be talking about organic acids. And that you guys need to pay attention to how we play with hydrogen in that regard. Okay. Okay. We know that we can share electrons, and the concept of sharing electrons is forming what type of bond? Covalent. Okay. So here we have fluorine and fluorine. We know that they're more stable by forming a dimer, right? So it forms a single bond between the two that they're sharing that electron. Same thing with hydrogen. Okay, so again, we know that we are fulfilling our octet by filling out that outer shell, by sharing that electron, right? Okay, tell me, everybody's good on this. This is all stuff that we've done, right? You're feeling comfortable, nothing crazy. Okay, so we know also that everybody wants to have their octet filled. In the case of when we're dealing with, let's say, the formation of water, okay? So in this case, it's going to take those two hydrogens. Each of those hydrogens have one electron to share. And then we have oxygen, which has how many valence electrons? 6 valence electrons. And so we just play around with it till everybody has their octet full, right? What is one way that we can ensure that we have the most ideal structure? Formal charge. Do you guys remember how to do the formal charge? That is correct. Number of valence electrons minus the number of bonds minus the number of pairs. All right, that's impressive. Okay. So polar and nonpolar. What is the difference between polar and nonpolar? Polar means what? Are they sharing evenly or unevenly? Unevenly. So if it's a polar molecule, they're sharing unevenly. That means that one guy gets it more than the other. And if we break that down in terms of electronegativity, the one that has the most electronegativity is going to have a stronger pull. Okay, so oxygen has a stronger pull than hydrogen because it's more electronegative than hydrogen is. Okay, so nonpolar basically means that we have even sharing, right? And so that basically means that they have either similar or the same electronegativity. They both have the same type of pull. Okay, so if we take a look at carbon and hydrogen, we know that carbon and hydrogen are about equal in terms of pull. I think one is 2.2 and one is 2.4. So there's very little difference between them. So they're going to form a nonpolar bond. Okay. Piece of cake? Good. Okay. Am I going too fast? This is kind of slow because you guys have already done it, right? So if I give you the test today on this part, you guys will ace it. Okay, so I hate this because every book has a different number that's associated with this range. Theirs is about the same. If it's less than 1.5, it's going to be nonpolar. If it's 1.5 equal to 1.5 or greater, but less than 1.9, then it is going to be polar covalent. And then if it's greater than 1.9, then it's going to be, they're going to show what they call ionic characteristics. Okay. Now, the reason why they say ionic characteristics, they don't want to say it's an ion because you have certain cases where you have such a huge gap between the electronegativity between two nonpolar, two nonmetals, that they act as if they're forming an ion rather than forming a covalent bond. Okay. Are you guys with me? Okay. Okay. And so this is their nice, beautiful scale showing you the differences. So we've talked about dipole moments. What is a dipole moment? All the dipole moment is. We've talked about it, but when you calculate the difference between electronegativity, that represents your dipole, right? And so that gives us a quantitative way of looking at whether or not things are going to be electronegative or electropositive. So by taking the difference between the two electronegativities, we get those values that falls within here. So this gives us our dipole moment. Okay. And so if you guys take a look, so I guess I over-exaggerated. The difference between hydrogen and carbon is 0.4. So we know, is that polar, nonpolar? It'll be not polar, okay? The difference between hydrogen and nitrogen is 1.3. Polar or nonpolar? Polar. Let's see. The difference between carbon and fluorine is 1.6. Polar or nonpolar? Okay, so and then we know that in that case, it's going to favor carbon or fluorine. Who? Fluorine, that is correct. So the electron is going to be on fluorine side more than it's going to be on carbon side, right? Because fluorine is the better parent. Okay. You guys see that because it has a stronger pull, more attraction. It does have a dipole moment. It's just not as strong. Yeah. Yeah. So the hydrogen and carbon does have a dipole moment associated with it, but it's a very, very weak dipole moment. So it's almost negligible. So, okay. Questions? Concerns? Can I get that, please? Yes. So typically, so the bigger difference between the two, the greater the dipole moment will be, except for when you get into the ionic characteristics, right? Because then it becomes like just like an ion, right? So then it's like that has a whole charge. It's taking the whole electron completely. Like, that's mine. You're not even worth my trouble, you know? Okay. Questions, concerns, Cash. Okay, so this basically is a nice little depiction of it. So you guys can kind of get an idea what it looks like. So in this case, we have lithium and hydrogen, right? So if we have lithium and hydrogen, who's going to be the favorite guy? Lithium. You sure? That is correct. It's going to be hydrogen, because in this case, hydrogen is going to be taking the electron away from lithium. Okay. Although it's kind of weird, right? So this guy, that means the blue means it's going to have a positive potential. It's going to have a plus charge associated with it. The red means it's going to have a negative charge associated with it. So if we look at it, oh, the hydrogen is going to be more negative. Okay, what about here with hydrogen fluoride? Okay, fluorine. That's right. Fluorine is like, he's the bully, right? You guys remember, he's like, that's mine. You're not going anywhere. Right? Okay. And then in the case of hydrogen and hydrogen, it's evenly shared. So it's like, oh, they're okay. Okay, Lewis structures. How you guys feel about Lewis structures? Okay, so you guys know that this represents your bonding pair, and these are your lone pairs. So if we were calculating, let's do this. We want to see if this is the best structure for a hydrogen peroxide. So how would I calculate the formal charge? For this guy. Okay, so let's start with the hydrogen. Okay, it's valence electrons. How many valence electrons does hydrogen have? So that is one valence electron minus the number of bonds. It has how many bonds? One, minus the number of lone pair, 0. And then the oxygen, say that one. 6 valence electrons. Okay, number of bonds, 2 bonds, and 4 lone pair. And what's the rule? It has to be 0. It needs to get as close to 0 as possible. Yes, so you're right, sort of, yeah. So you want to be as close to 0 as possible. So we know that this oxygen is going to have the same formal charge as this one here, and this hydrogen is going to have the same. Okay, so in all this case, they're all zeros. We know that that is a beautiful structure, right? That's going to be the most probable structure that it has. Okay. Okay, you're going to want to make sure you remember the formal charges, because you guys are going to be working with organic material and you're going to have a lot of options, right? And then some of those options are going to be valid options. They're going to be called what we call isomers. Do you know what an isomer is? Isomer. That's right. So we have the same chemical formula, but different structures. We're going to add another layer to that. We're going to have what we call stereoisomers. Stereoisomers are basically the same chemical formula, and it almost looks like the same structure, but a lot of times they're mirror images of each other. It's kind of like the left hand and the right hand facing each other, mirror images. But if you put them in the same, my thumb is over here. Right? Okay. So we'll be playing a lot with that. Okay, so you want to be familiar with that. And you guys all have your 3D model kits. Everybody got one from Mesa? Yeah. You get in the habit of bringing it. Today, you're not going to need it because we're still going over just general chemistry, right? And then, but next week when we start getting into organic chemistry, I want you guys to start bringing it, because a lot of times they're going to have you pull up a model or an image so you guys can see it. You know, it's like, if I had it to do all over again, I would make sure I brought mine every day, you know, because we would always go with these damn structures. And okay, I can't, I have a hard time with 3D structures. I don't know about you guys. I have a really hard time, particularly if they're on a piece of paper. I can't visualize it. So by having the structure there, it makes, oh, I see, you know. Yeah, yeah, exactly. Yeah, I hate it when, oh God. And when we start talking about vectors, because it's all deals with that 3D structure. And you're like, what the fuck? You know, just like, I can't see it, you know. So, sorry. Just being honest. Okay, so we've already talked about formal charges. We're ahead of the game. Look at that. Imagine that. Okay, so let me clear this out. We know that carbon can form 4 bonds, right? And so it can form 4 single bonds. It can form 2 double bonds on each side. It has flexibility, right? And so this here is basically, this is methane. This is showing you that it's showing you the different bonds. Here, this is the methyl cation. So basically, it's that methyl group that has a plus charge, right? This here is the methyl anion. This is the methyl radical. It means it has that free electron that is able to do crazy stuff. cause havoc. And then here, this is ethane. Okay. So if let's see. All right. Okay. Sorry, a couple students got a little confused because they heard through the grapevine that I wasn't here for my first class, so they thought we didn't have class. Okay, so we also have nitrogen. Nitrogen is going to be able to form 3 bonds, right? And so we think about the nitride molecule. Not nitride, ammonium. You guys remember ammonium, the ammonium ion? So we know that the ammonium ion down here, we have that extra hydrogen is that plus. Okay, so ammonia, right, with 1 lone pair. This is called hydrazine. Basically, it's 2 nitrogens that are bonded together, and you have the 2 lone pairs. So it's like 2 ammonias that are coming together, and you're losing your hydrogen, one of your hydrogens off of each one. Okay. So we know that they're going to form typically 3 bonds, and they typically have that 1 lone pair just kicking in and in. Now, occasionally we do have that case where we have that ammonium ion, and then here we have 2 lone pair. That means that we added an additional electron to it, which causes the amide ion. Okay. We know that oxygen forms 2 bonds, right? At most, it can form 2 bonds. Okay. So here we can see, in the case of hydrogen peroxide, we have 2 bonds, one between the hydrogen, one between the oxygen. We know that if oxygen is bonded to, let's say, carbon, yes, like this. So like in methanol, this is a screwed up picture of methanol. So our carbon is able to have that 4 bonds. That oxygen is able to sit there and have the 2 with the 2 lone pairs sitting on top. Okay. Okay. Questions, concerns? Cash? Okay, good. So as we can see down here with water, again, 2 lone pairs, each bonded here. Here we have the hydronium ion. Here we have the hydroxide ion, and here we have the hydrogen peroxide. And so we can see with the hydroxide ion, we're adding that additional electron to it. And then hydronium ion, we actually are losing a single electron. Okay. So basically we added that H plus to the water molecule. Do you guys remember hydronium in acids? We often write it as H3O plus. Remember that? Okay, so we know that when hydrogen is with 1 halide or a halogen, it's going to form a single bond. The halogen is going to have 3 lone pairs. And it's going to be important that, again, you pay attention to the pairs, because a lot of organic chemistry relies on those pairs attacking the molecule. right? Those lone pairs are going to be involved in reactions, okay? So we know that they're not involved in that particular one, but it frees them up for those reactions to occur, okay? Okay, so we know that in the case of the hydrogen ion, it's just H plus. The hydride ion, we add an additional electron, so it's H minus. This is the hydrogen radical. It has that one electron and it's able to sit there and go buck wild on people. This is the bromide ion. And then this is the bromide radical, where it has that free electron to react. Okay, we know that hydrogen and, say in this case, these radicals. We know that hydrogen and bromide are both, what type of elements are they? Yes, remember. Well, they're both gases. Bromine is a gas and hydrogen is a gas. They're diatomic. They're diatomic, right? So we don't really see the hydrogen radical, right? And part of the reason why we don't really see the hydrogen radical because it's radical, right? It's going to react with stuff. And so they prefer to be attached to each other for stability purposes. That's the same thing. Okay. And if you think about it, it's the same thing with all of the halides or halogens, I should say halides. Okay. How are you guys doing? Are you brain dead yet? Still? Okay, good. Okay, so if we're going to determine, like in this case, if we have carbon, it's bonded 4 times, and often, we have 4 different attachments, right? So 4 bonds that are here. We know that this carbon has how many lone pair associated with it? What was that? None. Okay. Here, this guy has 3 bonds and a lone pair, so it's going to add up to 4, right? And if you notice, everything here adds up to 4 essentially at the end. Okay. So the reason why it adds up to 4, why would it add to 4? The combination of lone pairs and what was that? Because it's a filled octet. Stability, right? It's like the noble gas. Because we know that noble gases, except for helium, say argon, if we drew it, it would have 4 lone pairs or no lone pairs, right? Okay. Okay. So at the end of the day, again, it boils down to being like the noble gases to have that stability. And we know that hydrogen only needs 2 lone pairs around it. So, okay. Questions, concerns, Cash? Tell me if I've said anything that you guys don't remember. Nothing? Good. Okay, so here we have Lewis structures. So this is a halide. This is an alkaline halide. To be exact, this would be the bromomethyl, bromomethane. Okay. You'll notice carbon has how many attachments to it, or how many bonds? 4. Okay. So the key is that you want to keep track of the number of carbon, or say, number of attachments that carbon has. So if carbon is going to be forming a double bond, is it going to be forming a triple bond? Is it going to be forming a single bond? Okay. So here we have all attachments to single bonds. Okay, we're also going to start playing with how to draw it in terms of organic chemistry. So structures. We touched on it briefly, but we're going to go into it a lot more. Okay. Okay, so again, we're going to use those Lewis structures to sit there and help us figure out things, but we're going to start cheating and drawing them in an organic way. Okay, and we'll talk about that when we get to that point. Okay, you guys are all familiar with how to do a Lewis structure, right? Yeah, no, maybe. Okay, so let's do, what is the name of this polyatomic ion? Nitrite. Okay, so who's going to be the center atom? What was that? The nitrogen is going to be the center atom. Okay, so nitrogen is going to be in the center. How many valence electrons does nitrogen have? 1, 2, 3, 4, 5. So it has 5 valence electrons. Oxygen has how many valence electrons? And we have how many oxygens? If I can write. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5, 6. Okay, this tells me what? It has 1 more electron. Okay, so is this guy good? Is that a good octet? Is everybody happy? No, because we don't even have a bond shared over here, right? So how can we set it up so that everybody's happy? How about I bring these over? Different color. Bring these over. Okay, if I brought that over to the other side, and now we have something like this. I'm going to use lines now since I'm being lazy. You guys can see my dots. Sorry, I had to draw through. Is everybody happy? Not nitrogen? Okay, so what do we need to do to make nitrogen happy? Make one of them a double bond. So if we do okay. In a way, yes. Mm-hmm. Resonant structures. Resonant structures. Yeah. Yeah. So this guy forms what we call a resonant structure, right? Okay. So if we do the what is it called? Thermal charges, then what's going to be the thermal charge on nitrogen? How many valence electrons does nitrogen have? Okay, so it has how many bonds? 4. How many valence electrons? So it has a 1. And then this oxygen here. How many valence electrons? Oops. Lone pairs, I mean bonds. Lone pairs. And then one of these oxygens. 6 bonds. Lone pair. Okay, so this guy would be -1, -1. That guy would be a plus. Okay, so that would probably give us our best, unfortunately, right? Okay, and at the end of the day, it has to add up. We put in brackets. It would add up to the charges overall has to add up to that negative charge, right? Okay, questions, concerns? Okay, good. Okay. Okay, so these are two of the common structures that are going to be used, or should I say, some of the common structures that are going to be used in organic chemistry. We use the formula aspect of it, but this is also considered a structure because it kind of helps us understand where things are going to be located at. Okay, so this is called a Kekula structure. So it's just basically the Lewis dot structure without the dots. Okay, so you don't have to carry all the dots. And then the condensed structure is basically just how that structure is going to be formed without any dots or any lines. Okay. And you'll notice it's not the molecular formula because the molecular formula in this case would have just been C2H6, O. Right? But by having it in the condensed form, we're able to sit there and see how that structure is going to be made. We're going to have this methyl group here, we're going to have methyl group here, and we're going to be attaching it both to O's. Those in the center. Okay. You guys got that? Simple, not too hard. All right. And so similarly, the same thing is happening here. So this lets us know how this is organized. Well, one of these guys have to be a double bond, but they're both attached to the carbon, right? Both oxygens. And then in this case, same thing where the carbon is attached to the nitrogen. And this one is easy, so. Okay. Let's see. Okay, so this here is the Kekula structure. This here would be the condensed structure of that. Okay. Now, sometimes some programs will actually draw the line to let you know, okay, that's coming off of there. Okay. But that's not always the case. So you'll end up with a single line and then you'll have the things that are hanging off of it. Okay. So both of those, you'll see both of these in some programs that you'll be using. I have to think about what Chem 101 does, because I think it does a combination of both. So sometimes they do it like this, sometimes it'll do it like this. Okay. Okay, so in this case, same situation where you have 1, 2, 3, 4, 5, 6 carbons, right? And then rather than drawing the branch structures for each one, you just have CH3, CH2, 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 CH3. Or you'll see it drawn out like this, where it says CH3 and then CH2 4 times. Okay. And you will see in literature, you'll actually see it both ways. So some publications are notorious for that, which I hate because you can't really tell. Now, I prefer the line structure, right? Line structure is you're using each branch as a carbon. So in the case of a line structure, we will be talking about it later. Let's say we're talking about this guy, 1, 2, 3, 4, 5, 6 carbons. So then each point represents a line. I mean, each carbon represents the point of that line. So that's 1, that's 2, that's 3, that's 4, that's 5, that's 6. Right? So that would be our 6 carbons. 1, 2, 3, 4, 5, 6. Now off the second carbon, we have a bromine coming off. So that's 1, 2, second carbon, we have a bromine. So Br. Off the fifth carbon, we have a chlorine coming off. Okay. And you'll notice the hydrogens are understood. You don't draw the hydrogens out. Okay. So this here is a line structure, or what we call a skeletal structure. Okay. Skeletal because it's only just the lines, bare bones, right? Okay. How are you guys feeling so far? You don't want to throw stuff at me yet? So we can keep going? Okay. So what I'd like you guys to do here, if you guys can draw me the line structures of the next 1, 2, 3, 4 molecules. And when you have that OH, you want to put that OH because that's a special group. It's an alcohol group. So we want to make sure that we do that. Okay. You got that, Israel?
Yep.
Okay. And then we'll have one of you guys come on board and do it. Yes, all 4. 1, 2. Okay, Sampula, you do the first one. On the board, yeah. And Jesse, you do the third one. No, I should say the last one. And then Jessica, you do the second one. I mean the third one, sorry, the third one. Did I give you the fourth one, Jesse? Okay. Okay, good. Old age, yeah. Okay. Sorry. Yeah. For those who are at home. Okay. I'm trying to draw. Okay, so we have 1, 2. Yeah. So this is 1, 2, 3, 4, 5. 1, 2, 3, 4. And then so yep. Yes. The posture. This guy would be like a bat with a OH. Okay, piece of cake, no problem. Okay, good. So let's test you guys' skills for the next set. Did you get that, Israel? Just kind of change the page.
Yeah.
Okay, here we go. Okay, so we'll have Leah's going to do the first one. Cameron's going to do the second one. And Kayla's going to do the third one. The third one. The third one on the next page. Okay, so let's see. I'm trying to do it again. Okay, Kayla. Double bond. Okay. Piece of cake. Simple. Sorry. We have people at home trying to share. Trying to figure a way so that when you write on the board, I can get the same images up here. Okay. Okay, so clear. Now we're going to talk about skeletal structure. Okay, so skeletal structure, this is an example of the skeletal structure. So you guys should be able to go from the condensed structure to the skeletal structure, again, by recognizing that each one represents a carbon unless it's attached to something. Okay, so in this case, we have 1, 2, 3, 4 carbons, 1, 2, 3, 4 carbons, and then the bromine's attached at the end. So here we have 2 carbons, 1, 2, attached to the oxygen, and then that's attached to a carbon. Okay. And then here, this is kind of like what you had earlier, right? So we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. On that third carbon, we have that methyl group, which is right here, and then the OH group. If it's a ring structure, ooh, beautiful ring, right? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So pentagon. And then if it's, this is called the benzene ring. So it has alternating double bonds. So that's 1, 2, 3, 4, 5, 6 carbons with alternating double bonds in between. So that's the benzene ring. Okay. Questions? Concerns? Cash? Kool-Aid? See how we're doing on time. You're saying where? This one here? Top one right here? No, you wouldn't put an oxygen. Oh. So this here represents, on one side, this is an ether, right? So on one side, it has one functional group. On the other side, it has another functional group on the oxygen. They're both attached via the oxygen. So if there's a carbon here, what do you mean by it? Yeah. Yeah. Yeah, at each point. So you say right here, 1, 2. So no. So that is the connection at the oxygen. So it's kind of like here where the bromine is connected, right? So that's a carbon, and then it's connected to the bromine, right? So there's not a bromine, right? Carbon right at the end there. Does that make sense? Okay. Yeah, but that is one of the most common mistakes that students make. They'll sit there, they'll count 1, 2, 3, rather than recognizing that that's the attachment for the oxygen. Okay. Does that make sense with everyone? Okay, but good question. Let's see. Okay. Okay, so do you guys, this is gonna, okay. So do you guys remember when we were talking about hybrid structures? Where we're going to be combining the S and the P? structures, hybridized structures. Kinda. Okay, well, we'll see how much you guys remember. Okay, so you guys are familiar with the s orbital, right? Okay, so so this basically just represents what the s orbital looks like. So that would be the 1s. We know that the 2s would be bigger than 1s. 3s would be bigger than the 2s. If you actually take a look, right? So if the 1s could actually be in the 2s, because when we're talking about an atom, what happens is that the electrons are orbiting around, right? So if we have the 1s inside in the center, then this here represents the node, right? That would be between that 1s and that 2s, okay? So have you guys ever played with like a string or a rubber band? You pull the rubber band back and then okay. So that's kind of like what's happening, you know, with that resonant structures, right? So here's that string that's plucking. This here represents the node. So that's going to be a positive, that's going to be a negative. And so when you think about it, you have those electrons. Electrons are going to be occupying that space in between, right? So here, electrons are going to be occupying the space that's here. The ones that are in the 2s, they're going to be occupying this space here, right? So it's going to be kind of like that plucking in that space because they're constantly moving in that area, okay? So, but there can't be that crossover, right? Because that crossover can't happen. And so you have what we call that line, which is that node where that crossover event isn't going to happen. Does that make sense? So this part would kind of be like your 1s, your 1s and this flow. Your 1s and this guy would be like your 2s, right? And so you have that line, even though it's plucking, that line kind of represents that area that you don't have them crossing over with each other. Is that like you're not getting that resonance happening there? Because it kind of counters. Okay, so this goes back to that saying when we're talking about electromagnetic, we know that light consists of photons, and photons are an example of like electrons escaping and all that stuff. You guys remember that, the energy? Okay, so electrons are going to behave, they're going to have aspects, that dual particle theory, where it behaves like a wave and also behaves like a particle, right? So here, this is our p orbital, right? So if we look at our p orbital, we have the px, we have the py, and the pz, okay? So we put these guys on top of each other. We have one in each of the different orientations. Now, when things are overlapping, like in the case of hydrogen and hydrogen, they're both 1s. These guys form what we call a sigma bond. Okay, so, and that's basically end over end. Okay, and then if it's like this in the p orbital, it would be a pi bond. That's right. Okay, you guys remember that? I know it's a while, but if it's end over end, let's say we have p and an s, that's going to be sigma. Okay. Okay, so this is an example of hydrogen. This is the example of hydrogen. So this is hydrogen when hydrogen is independent of each other, right? This is the energy state that it's in. Now, when it starts to overlap, when you're getting them so that they're actually sharing, the two orbitals are overlapping with each other. So that's that sharing component. The energy starts to drop. soon as they come together and they share the bond, you're at your lowest point. That's your lowest energy point. Okay. So this here is our lowest energy compared to the energy that's associated when they're separated independently. Okay, so this is the reason why hydrogen forms a diatomic molecule, because it's lower in energy than if it's just the elements alone or the atoms alone. Okay, now this is also the smallest bond length compared to what you would have here. This is a larger bond length than this would be. Okay. Yes. So yeah, so they are lower, they're going to be in lower in energy. So that's the reason that you would want to do things like this, is to try to get the lowest state. Diatomics, they want to be at the lowest state possible. It also, remember, we're talking about those radicals. That radical causes that energy to be worked up. Right? And so it would want to react with something immediately. So you want to try to keep a low energy state if you can. So it's going to react with itself in a sense and form that bond. Okay. Okay, so the energy that's involved in dissociation to break them apart, we have to put in this much energy to sit there and break apart each of those hydrogens. So when we're doing a reaction, we need to somehow come up with enough energy to break out the bond between the hydrogen so that we can actually dissociate it so that we can form another bond with something else. Okay. So we talked about dissociation energy. I don't know if you guys kind of put that together, you know, that formation and the breaking apart. Okay. Come on. Okay, so this here kind of is going to help us understand how things are going to behave, right? So if we have two hydrogen atoms that are coming together, if they're in phase together, they're going to form a constructive combination. They're going to bond. If they're out of phase with each other, they're not going to bond. Okay. And so this is destructive, and you're going to have a node in between. Okay. Where this one, you don't. Okay. So remember when we talked about bonding and anti-bonding? Yeah. So this kind of touches on that area. Okay. That bonding and anti-bonding. Okay. I know we were just kind of whipping through here like crazy. Okay. So God, it's like psychic or something. Okay. So here's the hydrogen come together. So this would represent that constructive. This would represent the destructive or the anti-bonding. So that's bonding versus anti-bonding. The way that we represent it, we know that this is a, what type of bond is it? Pi or sigma? So that's a sigma bond. So this would be a sigma bonding. So you just put the sigma. And then here, this would be sigma anti-bonding. So all it is just sigma star. Star represents anti-bonding. So if we had another electron, that would go into that anti-bonding state. That means that those electrons are not going to be bonding with each other. Okay, they're not going to be shared. Okay, are you guys with me? You understand that? Okay. Okay, so we've talked about in the case of the pi bonds, right? So here we have two pi bonds, one going in one direction, one in the other direction. If we had only one, they're going to form that pi bond. So you're going to have overlap here and overlap down here. And then if there are more than one, these guys are going to form what they call anti-bonds. So they're not going to form a bond with each other. And so they're going to act independent of each other. Okay. Yeah, that look, Jesse. Are you sure? Comprehending? Yeah. I know it was a while, and it was like, trying to remember in your class, I think I rushed through this part like it's a hot mess. Hot mess. And so we know that these guys are pi. And if you guys pay attention, I kind of handed out the Greek letters because you guys are going to run into a couple of the Greek letters here. But you guys also know pi, right? Pi looks like. Not the little dish that is round. Pi. Okay, so let's go ahead and take let's say a 10-minute break, 15-minute break, give you enough time to run across the campus and grab a drink or whatever. I don't know where, but okay. You guys are good? 15 minutes, bathroom break, tea break, then we'll come back and finish this up. Okay, so let's get started. Everybody's back? You ready again? Yeah. But we're like this close. We're gonna have you guys, I swear. In the semester, you guys are gonna be able to get the degree one way or another. So, okay, so I forgot what we're doing. Okay, so we've talked about the pi bond and anti. Okay. Okay, so this is methane. Okay, so this is the structure of methane. This is the bond stick model. This is the space filling model. This is the electropotential map of methane. And you can kind of see it's kind of like very general. Everything is kind of like pretty much the same, right? And with the electrostatic potential. Now, we have 4 bonds that are attached to that carbon. All of those bonds have the same bond length associated with it. Not one of them is shorter than the other, right? We also know that all of the bond angles are exactly the same. What type of structure is this forming? You guys remember? Tetrahedral. And in a tetrahedral structure, what is the angle? You guys remember? Anyone? 109.5. That's right. Right where? Oh, I didn't see it, you know. Okay. So we know that it's all 109.5. Okay. Now, for this to happen, we have to go through what we call hybridization. Okay. During hybridization, what's going to happen is that we're going to combine what we call our s and our p orbitals, so that we would end up with 4 orbitals that are equally potential. So then things are exactly the same bond length. Okay. So it's going to take the s orbital. It's going to take the 3 p orbitals. It's going to blend them together, sort of. And then you end up with our sp3 orbital. Okay. So that carbon, that center atom, forms that hybrid. And then that hybrid is going to interact with each of the hydrogens. So this is the combination of them all coming all together. This is what an sp orbital is going to look like, but they're all going to be comparable to each other. Okay. So here's our hybrid carbon, and that is it, forming sigma bonds with each of the sp3 orbitals. Okay. Do you guys get that? Yeah, no, maybe? Yeah, okay, good. Okay, so then that allows us to have the exact same bond length for each of the different orbitals, because if we didn't, the bond lengths would be different, right? Because where the p is located, I mean, the s is located compared to the p. So by us hybridizing those orbitals, we're allowed to sit there and have all of the bond lengths be exactly the same. Okay. Okay, so here, this guy is ethane. So we have bonds that are going to be happening between this carbon and this carbon. And then you have bonds between the hydrogens. Now, again, we're going to form the sp3 hybrids. So all of these technically would have the same length, right? Now, this guy is also going to form a sigma bond between the two carbons. Okay. Okay, so here, this guy was 105. Do you guys remember the angstrom of the bond length between the hydrogen and the carbon, since it was posted on the last one? Anyone? 1.1 angstrom. Okay, so this one is 1.5 angstrom because you have two sp orbitals that are overlapping together, where here you would have an s and an two sp3 orbitals overlapping together, and where here you'd have just the s and the sp3 overlapping. Okay, and since that s is going to be smaller, it's going to give you a smaller bond length. Okay. For letter A, that is angstrom. So it's a distance. So it's, let me spell it. See if I can spell it. Hold on. Are you there, Israel?
Yeah.
Okay. Okay. The number, so this, it's the distance, how far they're from each other. Yeah, it's bond length, right? So bond length lets us know how close things are together. Right? Okay, so we'll notice that the bond length here, which was 1.1 angstroms, right? And this one is 1.54 angstroms. So this has a longer bond length, which kind of makes sense because you have that sp, which is going to be a bigger bond than what you would have with just the s and that sp. So, okay. So this is the ball-stick model of that. This is the space filling model. This is the electrostatic potential. Again, you take a look at it, it's pretty much uniform. There's no favorites. Okay. Okay, so this here, oops, is basically showing us the filling of the hybridization. Okay, so this would be bonding. This guy's anti-bonding, so this is a sigma bond. This would be an anti-sigma bond. So each of them providing an electron to share. So we have a bonding molecule. It's able to come together to form a nice bond. Okay. For your sample, Jesse, you have that look. Okay. Now the key is that minimal energy, right? So you want to try to keep the lowest energy possible, right? So lowest energy possible that we can get. And okay. Okay, so this here is ethene, also called ethylene, a double bond between the two carbons. Okay, so we know that, where's my pi bond? Okay, so we have, in this case, we'll form 3 sigma type bonds. And then the last one This last P is going to be involved in the double bond. Okay. So these guys are going to come together. 1, 2, 3. You have 1, 2, 3 attachments. So you have sp2. So you have 3 sp2 orbitals. So those orbitals are going to be exactly the same. This P is going to be different. Okay. Okay, so this basically shows you the hybridization of that carbon. So now we have each one of those, there's 120, and then we have the P that's going to be on the top and the bottom. Okay, so we have SP, sp2 overlapping together. So you have from one carbon and the other carbon. We have the sp overlapping with the s of the hydrogen, the sp overlapping with the s of the hydrogen, and then the same thing on the other, this other end. Okay, so this guy is a sigma bond, and then those P's that didn't hybridize from each of the carbons are going to overlap to form that double bond, or form the second bond of the double bond. Okay, so this guy would be that first line. This here is going to represent the second line. Now, because of that, that's going to affect our bond. Okay, so do you guys remember the difference between, or the bond length between carbon single bonded to each other, carbon single bonded to each other? What was it? 1.54, right? Now we have that double bond. The double bond is going to be shorter, right? Because you have those two the two P's that are overlapping to form that pi bond, it's going to make a shorter bond. Okay, and so in this case, you'll have a 1.33 angstrom compared to a 1.5 angstrom. Okay, and you'll notice that we have changes in our angle. Okay, so this is the ball and stick model. This is the space filling model, and here you're starting to see a little bit of that potential happening. Right? Questions, concerns, Cash? Are you guys getting this? Is it making sense? Kayla, you have that look. Is it making sense? A little bit? Okay. Okay, so this guy is called ethyne, triple bond, or it's also called acetylene. Okay, so it's triple bonded between the carbons. So in this case, we're going to have 2 unhybridized carbons, 1, 2 that are going to be hybridized. So that's an S, and the P that's going to be hybridized. So we're going to form an SP hybridization. So what are you guys expecting? Are you expecting it to be a shorter bond length, or do you think it's going to be a longer bond length? I'm going to say shorter, shorter. Okay, let's see. Okay, so that's your 2 SPs, that's your P, this is your other P. So the blue represents the P, this pink or purple represents the other P. Okay, so if we look at it, okay, so we have the SP forming a bond between the S of the hydrogen and the SP of that carbon. The SP is also forming a bond with the other SP of the other carbon. Okay, and then the S of the hydrogen. And then we have 2 pi bonds that are going to be formed. That's pretty nasty. So we get the formation of our 2 pi bonds. There's one, there's the other. Okay. So our bond length is 1.20. So you're expecting it to be shorter. And that is exactly what you guys see, shorter bond length. But you'll notice that the angle is 180. Questions? Concerns? Kool-Aid? Good. Okay. And again, we look at that electrostatic potential. We're starting to see a lot more electrostatic potential occurring in this case. Okay, so this is an example of the carbon in the methylene cation and the methylene radical. So methylene cation, a cation is what? Positive or negative? Positive, okay? So we have a plus that's going to be associated with that carbon. We have those 3 hydrogens that are going to interact. And we know that those hydrogens are going to be interacting via those, the sp, 2, 3 attachments, so the sp2. And then in the case of that radical, so that's going to be our P. These are going to be SPs, SPs, SPs. And so again, we're going to have that 1 electron in that p orbital. Okay. So this guy, since there's no electron that's free to sit there and roam, the electrostatic potential map is going to be pretty much neutral, like 0. So just not 0, plus, all plus. Then here, since we do have this radical, we have a very dynamic electrostatic potential. It's going to be plus at the end, but that core, since we had that free electron that's going to be roaming here, then it's going to have that more minus component. Okay. That crazy component. So this here is the carbon in the methyl anion. So anion is positive or negative charge? Negative charge. So we would expect it to have an effect of being negative. So the same thing is going to happen. These guys are going to form the sp3. And then this guy, the lone pair, is going to be in one of those sp3s because the lone pairs are going to be included in that. So we're going to get this is the ball stick model for it. And then this is the electrostatic potential, where this is all negative and this is kind of that yellowish, but not bluish. So we have a more negative ion occurring. Yep. Right here? Yes, yes. Because the hydrogen is that S, the overlap, yeah. Because all the hydrogens are in the S shell, so that's going to be your overlap. Good question. Okay, let's see. So ammonia. So ammonia has 1, 2, 3 attachments, but there's also lone pairs that are going to be attached, right? So it's going to take, so that's 1, 2, 3, 4. So we're going to need 1, 2, 3, 4 orbitals to sit there and get all of them incorporated. So then this guy is going to be sp3, the hybridization that's going to form. Okay, so then we get 4 sp3 orbitals formed. Okay, do you guys get that? You know, so when you draw the Lewis structure, you should be able to predict the hybridization. And then also from the hybridization, you should be able to predict the Lewis structure. All right. Okay, so the distance between the hydrogens is 107.3, right? And so here, this is that lone pair. and then that is the sp3s overlap. Okay. And so in this case, we have electrostatic. So the hydrogens are going to be kind of bluish, right? Meaning they're going to be positively charged. And then over here towards those the electrons here, that's going to house most of our negative charge. Okay. Questions, concerns, Kool-Aid. Okay, so this is the ammonium ion. The ammonium ion, we're adding the H plus to it. So this guy's forming tetrahedral, right? So it's all going to be 109.5. So what is going to be the hybridization on the end, on the nitrogen? Is it going to be sp1? Is it going to be sp2? Is it going to be sp3? Is it not going to be any hybridization at all? sp3. Okay, so it's going to form 4 sp3. Okay. Okay, here's water. Agua. Okay, so oxygen is going to be that center atom. So oxygen has 2 valence electrons, and it has 2 bonds. So how many attachments total? 4. So it's going to be what? sp3. Okay, it's going to be sp3. That is correct. Okay, so then we're going to get 4 sp3 orbitals, hybridization orbitals. And then this is how it's going to go. So is that all making sense to you so far? Okay, so we're going to see. We finish these slides, then I'm going to let you guys go a little early, if that's okay. Because I only had planned to do these slides. Was that? That works out? Okay, good. Okay, so now we're going to talk about those hydrogen halides. Okay, so here we have hydrogen fluoride, hydrogen chloride, hydrogen bromide, and hydrogen iodide. You can see the difference between them is what? Visually, what do you guys see that's different between them? The size and color. Okay, what was that? Okay, so we know that as we go down the periodic table, what happens to the size? It increases. So if we're in the same group, we're going down, it's going to increase. So that kind of makes sense, right? Okay, good. Okay, so if we have HS, HF forming, and we have 3 lone pair, right? So what are we going to do? What type of hybridization are we going to have? sp3. Yeah. So we're going to merge them all together, sp3, even though you already have your lone pairs already established, so you're kind of good to go. So it's still going to be an sp3 hybrid that's going to form. So we're going to get 4 sp3, and that's going to happen in all of these cases. Yeah, it's going to happen to all of the halogens. Okay, so the difference is though, let's see, come on. So this is the HF, and so you guys can see the electrostatic potential. This is going to be the difference between them. So here, what happens to the bond length? The bond length is going to increase, right? So as we go down the periodic table, the bond length increases. Now the bond strength decreases. Okay, so that means that the hydrogen iodide is going to be weaker than the hydrogen fluoride. We know that, right? Because remember, we know that fluorine is a big ass bully. He's like, no, you're staying close to me. You're not moving. Sit right here, don't move, right? Where, you know, iodine is like, oh, come on, you're fine. Okay. Does that make sense? Okay. And it also makes sense because they're so big, you stop worrying about the people that are way out there, right? So, but if they're right next to you, you're like, oh, right here. Okay. Okay. So this actually gives you the numbers. So here are the bond length. So for hydrogen fluoride is 0.97. And then if we go to hydrogen iodide, it's 1.609. That is a big difference when we're talking about bond, right? Between those two. So bond strength, this guy has a much stronger bond, right? Hydrogen it is, you're not leaving me, right? Where iodine is like, do what you like, you know? Okay. Are you guys with me? You see that? And that's going to be a general trend as we go down the periodic table, down the groups. Okay. So you guys are familiar with molecular geometry. Remember what tetrahedral is? Yeah. Trigonal planar. Attachments, all in the same plane. 1, 2, 3, all in the same plane. Trigonal pyramidal. What does that look like? That's right. We have a lone pair up top, and then we have 3 bonds, and so it's pushing that down. So, okay, and linear, right? You guys are very familiar with single bond, double bond, triple bond. So in the single bond that you have is going to be a sigma bond. In the case of a double bond, you're gonna have 1 sigma bond, 1 pi bond. In the case of a triple bond, you have 1 sigma bond and 2 pi bonds. Okay. Questions, concerns, Kool-Aid. Okay. Okay, so if you take a look at this, if we drew these structures out, what is going to be the hybridization? Well, it already tells us the hybridization. So we know that there are going to be 3 attachments. Each of these are going to be attached. Each hydrogen is going to be attached to this, and that carbon is going to be attached to the nitrogen. Right? So when we do hybridization, we're always looking at center atoms. So we'll be looking at that center atom here, that carbon, and then we'll be looking at the nitrogen as if it was independent, right? And that's the same thing that's going to be happening over here with these guys. Questions? Yeah. Yes, because the lone pairs are going to be caught up in the hybridization. Yeah. Let's say we had a radical, right? So in the case of radical, yeah, so it's a good question. Yes, the radical would actually be caught up in that as well too, but you just have a radical there. Yeah. Okay. Okay, so we've already talked about bond strength and bond length. And so we know that if you have single bonds, those are going to be weaker bonds. They're going to be easier to break, right? And they're also going to be longer. So the longer your bond are, the longer your bond is, the weaker it's going to be. The shorter your bond is, the stronger it's going to be. And so as we go, if we have a single bond, weak. Double bond, it's stronger than the single bond. Triple bond is going to be the strongest because it's bringing everything closer together. Okay. So shorter bond length, weaker bond. I mean, shorter bond length, stronger bond. Longer bond length, weaker bond. Okay. Okay. Questions, concerns. Okay. So here we have a shorter bond length, single bond, right? Shorter bond length because you have an S and the sp3, okay, compared to an sp3 sp3, okay. This guy is going to have a longer bond length compared to that S and that sp3. So this guy is going to be weaker than this guy. Okay. So if you had something that was attacking this molecule, where's it going to break first? The shorter bond or the longer bond? Okay, and that kind of makes sense. The longer you are, that means you're able to get stuff in there, right? If you get stuff in there, you can break it, right? Okay. So this is just, again, showing us. So if we have SP, right? SP is going to be shorter and stronger than the SP2. And then the SP3 is going to be our weakest and our longest. Okay. So the more of the S character that you have, the stronger the bond is going to be. It's closer in that case. Okay. Make sense? Okay, so here we have sp3, sp2, sp. So the sp has a shorter bond length, right? Is it going to be stronger or weaker? Stronger. This guy is sp2, stronger or weaker than, let's say, the sp. It's going to be weaker. And then the sp3, stronger or weaker? Okay. Now, if we look at our angles, the bigger the angle, that typically means that we're going to have more S character. Okay. So as we go lower in our angle size, that's less S character. Are you guys there? Are you with me? I know we're all yawning, ready for a power nap. Okay. So this is just kind of summarizing everything that we've kind of talked about in terms of the ethane, the ethene, and the ethyne. Which one is going to have the strongest bond? The ethyne. Okay. Which is going to have the longest bond length? The ethane. Okay. Which is going to take more energy to dissociate? The ethyne. Okay. Oops, I got carried away. Okay, this is just a summary of everything. Okay, pi bonds. Pi bonds is weaker than a sigma bond. This is just basically showing you the numbers so you can see it. So typically your pi bond is broken first and then your sigma bond, which is interesting though, because to me, that wouldn't have been intuitive for me. Because if you look how pi bond is overlapping, it's overlapping at the two poles, right? Apparently. Okay, so dipole moments. So this here we have carbon dioxide. So if this is one dipole moment and then the other dipole moment is pulling the opposite direction at the equal strength, so then what happens in that case? Your overall dipole moment is going to be what? 0, because they're going to be opposing each other. So it's like somebody of equal strength pulling you on both sides. Nobody's going to win in that tug of war. Okay. Here, if we have carbon tetrachloride, in this case, we have chloride on each side. Everyone is pulling evenly. You have one pulling you here, one pulling you here, one pulling your leg, one pulling your head, all pulling evenly. What's going to happen? Nothing. You're not going to move, right? Okay. So total dipole moment. So So this here is molecular polarity. We've talked about that. You guys remember that? Okay, so if we have one chlorine here, all of these are hydrogens, right? Chlorine, we know, is more electronegative than our hydrogens. So the dipole moment is going to favor which way? And it's going to be pulling towards it. The chlorine. So if you notice, they have it all tilted so it's all going towards pretty much the chlorine. Okay. So in the case of water, it's going towards, both of them are going towards oxygen, right? So it's kind of like oxygen is pulling the hydrogens themselves. So the dipole moment is going towards the oxygen. And in the case of ammonia, we have one. Okay. Questions, concerns? Cash. So this also helps us explain that static electrostatic potential, right? Okay. That's it. You're all done for today. That was very efficient. Okay, so I'll see you guys on Monday.